Hi everyone, welcome back to another chemistry video. Today we're going to be talking about phase change and IMFs. So let's start with question 1. Which of the following best describes the intermolecular forces present in liquid bromine? So I find with these types of questions, it's very helpful to kind of draw out the molecule. So this is bromine. And we're asked which intermolecular forces are present in this molecule. So there's 3 types of intermolecular forces that we learned. Number 1 is London dispersion forces, or LDFs, and these are always going to be present because they are the random movements of things within the molecules that create these instantaneous dipoles. And then number 2, we have the dipole-dipole, which occurs in asymmetrical molecules. And basically what this does is it creates an electronegativity difference. Well, there's going to be a difference between the two different atoms when you have an asymmetrical molecule, meaning that one side will attract more electrons than the other. And then this creates a partial positive or negative charge, which you may have seen is like a delta minus or a delta plus. And then it's these partial charges that are going to be the forces that occur between molecules, and this happens with polar molecules. And then number 3 is the hydrogen bond. And this is when you have hydrogen bonded to either a nitrogen, oxygen, or fluorine atom. And these are also listed in the order of strength, so it gets stronger as we move down. So it doesn't have hydrogen bonds because we don't have NOF. It can't be dipole-dipole because it's not a polar molecule. And as you can see, it's just two BRs connected, so it's symmetrical and nonpolar. So that means all that we're left with is going to be the LDF. So the answer is London dispersion forces only. Question 2. Which of the following pure substances is capable of acting as both a hydrogen bond donor and a hydrogen bond acceptor? So once again, I find it really helpful to draw out the molecules. So for the first one, it's going to look something like this. So we have an oxygen in the middle and then 2 carbons, and then this oxygen will have 2 lone pairs. For fluoromethane, we'll have a C in the middle, 3 H's attached, and then a fluorine. For ethanol, I'm not going to write the H's anymore because that's going to take too much time, but when you see a line here, just assume there's an H attached. This one has an oxygen attached to a hydrogen. And then for methylamine, the last one, it is carbon with a nitrogen and 2 hydrogens and a lone pair. So let's first define what a donor and an acceptor is. So we've already established that H must be bonded to oxygen, nitrogen, or fluorine. So we can automatically eliminate right now the first 2 options because there's no hydrogen that's being attached to O, N, or F. And then an acceptor is basically a lone pair that's on O, N, or F because that's going to attract the partial hydrogen, a partial positive hydrogen, and then the donor is the H that is attached. So basically, in this case, we have the O being the acceptor because it's going to accept a hydrogen, and then the H is the donor. And then with this example, the N is the acceptor, and then we have H as a donor again. So this one acts as both an acceptor and a donor, which this is not correct. So we can say that it's C. Okay, question 3, rank the following in order of increasing boiling point. They are all nonpolar, tetrahedral, and group 14 hydrides. So once again, let's go over the intermolecular forces, because once again, with boiling point, we know that the stronger the intermolecular forces, the higher the boiling point, because it's going to require that extra energy to break apart the intermolecular forces. So looking at all of these molecules, they don't have O, N, or F, so we can say that there's no hydrogen bonding, so we don't have to worry about that. And then with dipole-dipole, we have no dipole-dipole, because once again, dipole-dipole only happens with polar molecules, and the question stated that these are all nonpolar. So basically, what we have to look at is LDFs. So with LDFs, this is going to depend on the mass of the molecules, because the larger the molecule, the more random movements there are within the molecules, and this will create more and thus stronger instantaneous dipoles, which will lead to a stronger intermolecular force. So molecular mass, these all have 4 hydrogen atoms, so the only thing that differs is C, silicon, and germanium. So we just have to look onto our formula sheet and make note of which one is going to be heavier than the others. So germanium is here, silicon's here, and carbon's here. So germanium's the heaviest, then silicon, and then carbon. This is 32. This is number 14, and then carbon is 6. And then as we move down, because it gets lighter, it will have a lower boiling point because they have not as strong London dispersion forces. So the answer is B. Question 4. A student compares 1-butanol with diethyl ether. Both are constitutional isomers with this formula. What best explains the large difference in boiling point? So once again, boiling point has to do with IMF. I find it helpful to draw out each of the molecules. So I'm not going to write out all of the carbon chains. I'm just going to do like a dot 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 and then show the alcohol group, which is O attached to an H. So that's 1-butanol. And then diethyl ether is going to be an oxygen in the center of the 2 carbon chains, and it will look like this. So let's look at what IMFs are present. So in this first one, we have a hydrogen attached to an oxygen, which indicates that there is hydrogen bonding, right? We have the donor, which is the hydrogen, and then the acceptor, or the lone pairs on the oxygen. And then let's look at diethyl ether. This one does not have hydrogen bonding. We have an acceptor here because there's an oxygen with lone pairs, but we don't have any hydrogen attached to it, which can be the donor. So because we don't have a donor, it can't create hydrogen bonds within itself, and, or I guess I should say between molecules, there's no hydrogen bonding, which means that 1-butanol is going to have stronger IMFs, and this results in it having a much higher boiling point. So this is option B. Question 5. What is the maximum number of hydrogen bonds that a single molecule of methanol can form with neighboring methanol molecules? So once again, let's draw out what methanol looks like. So that's methanol. And then let's mark out where we have the donors and acceptors. So we have 2 acceptors here and 1 donor here. And the maximum number of hydrogen bonds is just going to be the number of sites for donating and accepting, I guess. So in this case, there's 3. So then the maximum number is just going to be 3. However, this differs from the average number of hydrogen bonds. So this one we're talking about maximum. This one we're talking about average. So question 6 is the average number of hydrogen bonds per molecule in bulk liquid HF is 2, even though a single molecule has 1 donor and 3 lone pairs, giving a maximum of 4. So that would be the maximum number of hydrogen bonds, but the average is 2, and they're asking, why is the average lower than the maximum? So in the slideshow, or you will have learned that the average is 2 times LR, which stands for the limiting resource. And what this means basically is I'll give an example. So for example, with hydrofluoric acid, we have a donor over here. We have 1 donor, and then we have 3 acceptors. So what's limiting is the minimum number of donor acceptors. So here we only have 1 donor, and this is the limiting resource. So that's what LR is in this case. But then, for example, with water, we would have 2 donors and also 2 acceptors. So the minimum is 2. So then the limiting, or the LR, is going to be 2. That's basically how you find the limiting resource. And then you multiply 2 because each bond involves 2 molecules. So if we go through our options, A does not make any sense. B is correct. In the bulk liquid, the limiting resource restricts the average number of hydrogen bonds, since every hydrogen bond requires 1 donor and 1 acceptor. So that's the reason why the average is lower than the minimum. Okay, question 7. Which of the following correctly ranks NH3, pH3, and ASH3 by increasing boiling point? So NH3, let's list out all of the IMFs that are present in each of these. So NH3 has hydrogen attached to nitrogen, which qualifies for hydrogen bonding. pH3 and also ASH3, these ones don't have hydrogen bondings, so we have to look at which molecule is bigger and thus has the most London dispersion forces. So we look at size for both of these, and let's compare phosphorus and arsenic. So arsenic is larger, and therefore it will have stronger intermolecular forces than pH3. So the order should be pH3, ASH3, and then whatever has the hydrogen bond is going to have the strongest IMF and also the highest boiling point. So this is option B. Okay, question 8. At 25 degrees Celsius, delta Gibbs energy is 2.1 kilojoules per mole for the vaporization process, Br2 liquid, Br2 gas. What is the vapor pressure of Br2 at 25 degrees Celsius? So with these types of questions, the formula you're going to use is this one. Delta G equals negative RT ln K. You will have learned this in the last course because we're trying to find K using the information that we have. So for delta G, we can sub this in. Very important, we want to make sure it is in joules per mole and not kilojoules per mole, because this value that we use for R, which is a constant on the formula sheet, is in joules. So we have to make the units equal to each other. So it will be negative 8.314, the constant, and then T, which should be in kelvins. So that's 298 kelvins ln K. And then calculate this, solve for K, and you'll get 0.428. And then what is K? K is products over reactants. So it's the pressure of the gas over the concentration of the liquid. And then this is just partial pressure of the gas over 1, because as we learned, this is in standard state, so we just put 1 over here. And then the rule that we should remember is that vapor pressure equals equilibrium partial pressure. Or we could write it as K equals the partial pressure of the gas. So this means that the vapor pressure is just equal to K, which is 0.43 bars. So then it's option B. Okay, question 9. Using the vapor pressure versus temperature diagram style shown in class, which compound would have the lowest boiling point at a fixed external pressure of 200 millimeters of mercury? So they talk about this vapor pressure versus temperature diagram. That is the one that looks like this. So it has a curve kind of like this, and then we have temperature on the x-axis and vapor pressure on the y-axis. And then I'm going to draw 2 different graphs just so it's easy to compare the effects of each one. So these options are like 200 at the lowest temperature and then 100 degrees Celsius. So I'm going to label all of those on the graph. So I'll say 200 is over here, and then let's make 100 degrees over here. And then I'll draw a line. And then basically what this graph is, on the left side of the curve, it's liquid state, and then on the right side of the curve, it's in a gas state. So the compound whose curve crosses 200 at the lowest temperature has the lowest boiling point. This is going to be true because a lower boiling point, basically if the boiling point equals, or I guess we'll say boiling happens when the vapor pressure equals external pressure. That's when boiling happens. So a lower boiling point should be a lower temperature when it reaches the external pressure of 200. So that means, like, between which one of these, which one would have a lower boiling point? It is the one on the left. And then that means B is wrong. And then the compound with the highest vapor pressure at 100 degrees Celsius. So this is 100 degrees. If you go up, you can see that the one on the left has a higher vapor pressure. So then both A and C are correct. And then the answer will be D. Question 10. A sealed vessel containing liquid water at 25 degrees Celsius is connected to a mercury manometer. If the temperature of the vessel is decreased to 10 degrees Celsius, what happens to the mercury level difference and why? So this mercury manometer that was in the slideshow, I'm going to draw it out right now. So it looks something like this. And then this little bit is water, and then we'll have some liquid water, but then also some in the air. And then this creates pressure that pushes the mercury to a higher level. So this is the manometer. Now, right now it's at 25 degrees Celsius, but we want to decrease it to 10 degrees Celsius. So let's see what that will look like now. So if the temperature is decreased, there's going to be more liquid and less gas. And then because the vapor pressure decreased, because the temperature decreased, that means there's less pressure pushing this mercury upwards, and then the mercury level is actually going to go down. And it will become more level because there's less pressure from the water side that's pushing it upwards. Okay, so this means that the correct answer is B. The difference decreases, so it's becoming more level because the vapor pressure decreases with decreasing temperature. All right, question 11. Which of the following correctly ranks 1 propanol, 1 butanol, and 1 pentanol by increasing viscosity at room temperature? So basically this is making us look at the LDF difference between all of them. And an important thing to note is that all of these are pretty much the same, except they all differ by one thing, and that is another carbon or a CH2. And then having an extra carbon or an extra CH2 is obviously going to increase the mass of the molecule. So what is viscosity? Viscosity is a liquid's resistance to flow. So having a high viscosity means it's very thick and hard to pour, which means that there is a stronger intermolecular force between the molecules. And the intermolecular force that we're looking at is LDF. And then what causes increased LDF? An increase in molar mass. So the heaviest one is going to have the highest viscosity, and the heaviest one is pentanol because there's 5 carbons, 4 carbons, 3 carbons. So that's the order. So it should be pentanol first, butanol, and then propanol. So, or increasing, so it should be option B. Question 12, which of the following statements about viscosity is false? So A, honey has a higher viscosity than water because it has stronger / more extensive intermolecular forces. This is true. Viscosity depends on intermolecular forces, so therefore honey has more than water. B, branch alkanes typically have lower viscosity than linear alkanes of the same molecular formula due to reduced surface contact area. This is also true because if you look at a branch or like a linear setup versus a branched one, the linear one is going to have more surface area to be in contact with another linear molecule. Whereas for this one, it's going to be a little awkward and not have as much surface area between the two. And then because there's a lower contact area, it's going to have weaker London dispersion forces. So there's less space for LDF contacts. C, viscosity decreases with increasing temperature because increased kinetic energy helps molecules overcome intermolecular forces more easily. This is true. Like when you think about heating up something, it tends to flow better, and that's because when you increase it, more energy, and then it can overcome the forces. Pretty self-explanatory. And then that means D is correct. Viscosity is a measure of a gas's resistance to expansion. This is obviously not correct. It is a liquid's resistance to flow. Question 13. Which of the following phase transitions is exothermic? So an important thing to know is I'm going to draw a diagram that's going to make this really clear. So I have solid here, liquid, and gas. So all reactions that move in this direction, so they become more gaseous or they become less solid, I guess, all of these are endothermic because it requires energy to break those IMFs and thus turn it into a liquid or a gas from a solid. And then all the reactions that go this way are exothermic because it's releasing energy by allowing for those IMFs to form. So if you look at sublimation, sublimation is solid to gas. And then solid to gas, we're moving this way in the endothermic direction. So this one's endothermic. Melting is solid to liquid. So we're moving this way again in the endothermic direction. So this is not it. Deposition is the opposite of sublimation, which is going from a gas to a solid, which is moving in this direction. So this one is exothermic. And then let's just look at evaporation. Evaporation is liquid to gas. So it's also moving in the endothermic direction. And just a tip, if you're a bit overwhelmed by all of these definitions like sublimation, melting, I would say that 4 of them are very obvious, or you could figure it out yourself. Like they're pretty self-explanatory. The only ones that are more difficult to remember are sublimation and deposition. So as long as you remember those two, you should be good for all of these phase transition names. Question 14. Sweating helps cool the human body. Which statement correctly explains why? So A, sweat evaporation is exothermic, releasing heat that warms the skin. So let's look at evaporation. We just talked about this in the last question. Evaporation is liquid to gas. And as we said, when it moves this way, it becomes more gaseous, or less dense, I should say. When it becomes less dense, it's going to be endothermic. So this is not exothermic. So that's not it. B, sweat evaporation is endothermic. This is correct. And the energy needed to overcome IMFs and vaporize the sweat is drawn from the skin, cooling it. This makes sense, and that's the correct answer. Let's look at C and D. So sweat has a very high vapor pressure, which traps heat near the skin. This one, you don't really have to think about it. It says traps heat near the skin, which would not cool you. It would just make you hotter. So this can't be it. And then D is kind of the same. It says sweating prevents the boiling point of water, or it increases the boiling point of water on the skin, preventing heat loss. Preventing heat loss also would not cool you. It would just make you hotter. So this doesn't make sense. So it has to be B. Next, 15. refer to the phase diagram of CO2 with a triple point at this point and a critical point at this point at 1 atm or 101 kilopascals pressure. What happens to solid CO2 as it is warmed from negative 100 degrees Celsius to 25? So this phase diagram that they're talking about is the little tree one that we saw, kind of like a tree or a Y. It will go up here and form kind of like a Y like that. And temperature on the x-axis, vapor pressure on the y-axis. And then what this tells us, this portion here is liquid, over here is solid, and then over here is gas. That's how you read the phase diagram. So they say that a critical point near 31 degrees Celsius, so critical point is the point where the line between liquid and gas ends. So that's over here. And I'll label this 31. And then the triple point is near negative 57. So the triple point is exactly what it sounds like. It's over here when all of the phases are in equilibrium. And I'm going to label that negative 57. And then this happens at 518 kilopascals. And then this critical point happens at 7,380. I know the proportions are a bit off, but it doesn't really matter. They're asking at 101 kilopascals, which would be around here, what happens to solid CO2 as it is warmed from negative 100 to 25. So I'm going to put negative 100 around here, and then 25 would be around here. So it's at this pressure, it's being warmed from negative 100 to 25. It's going from this point to this point. So what happens here? It goes from solid, because this point is in the solid region, and it goes to the gas region. So this means that it's option B. It sublimes directly to a gas without ever forming a liquid, because it doesn't pass this point. If it went like this, it would mean it has to go to liquid first in order to become gas. Down here, it's just sublimation. 16. Which of the following is true at the critical point of a pure substance? So the solid, liquid, and gas phases are all in equilibrium simultaneously. This is not true. This is the triple point, not the critical point. B. The densities of the liquid and gas phases become equal and the interface between them disappears. This is correct because the critical point, as we said, is over here, and it's when the boundary or the line between liquid and gas goes away. And then once you go beyond this point, the liquid and gas phases are equal, and then there's no separation between them anymore. So in the slideshow, I think there was an example where you could see one part and there's clearly liquid here and then clearly gas here, but then when it becomes a supercritical fluid, it's just kind of all one thing and the interface disappears. C. The vapor pressure of the substance becomes 0. This is not true. The substance can no longer exist as liquid or gas, only as a solid. This is also not true. So it's B. 17. Which of the following is a genuine advantage of using supercritical CO2 as a solvent compared to a traditional organic solvent like tetrachloroethylene? This one is just going to be B. This was in the slideshow. Supercritical fluids will avoid the release of chlorinated compounds and is more biocompatible. So basically just more eco-friendly. Question 18. A phase diagram shows the solid liquid boundary with a negative slope leaning slightly to the left as pressure increases, as observed for water. What does this indicate about the relative densities of ice and liquid water? So this is once again the phase diagram that looks a bit like this. Let me draw it better. Kind of like this. And then this like boundary, the solid liquid, remember solid is here, liquid is here, the boundary is a negative slope. So this is what they're talking about. Over here. This is the negative slope. And they're asking, what does this indicate about the relative densities of ice and liquid water? So remember that vapor pressure is here and then temperature is here. At the same temperature, so this is ice in the solid region. And then if you want to go to liquid or water, you have to go up. And when you go up to the liquid, you're going up vapor pressure. So up here, it's denser than down here. And what this indicates is that ice is less than water. Okay, question 19. Second last question. Which of the following correctly ranks CCl4, CBr4, and CF4, all nonpolar symmetric tetrahedral molecules, by increasing standard enthalpy of vaporization? So remember that when we increase IMF, we're also increasing the standard enthalpy of vaporization. So when we order it from increasing delta H, it's just going to be ordering it by increasing IMF. And once again, I don't see, there's no hydrogen bonds, right? Because we don't have any H attached to any of these. They're all nonpolar, so we don't have dipole-dipole, and they're symmetric, so we don't have dipole-dipole. So all that matters is LDFs once again. And then remember what impacts LDFs, it's the molar mass. So we have Br, F, and Cl. So Br, F, Cl. So bromine is going to be the largest molar mass, and then fluorine is going to be the smallest. So we order it like this. So it's A. Final question. Which statement about IMFs and biological structures is false? A. Hydrogen bonds between complementary base pairs help hold the two strands of DNA double helix together. This is true. I think everyone learned this in biology class, but we have hydrogen bonds between purines and pyrimidines, which keep the double helix together. B. The hydrophilic phosphate head groups of phospholipids interact with water primarily through ion-dipole interactions. This is also true. So ion-dipole means there's one partial positive or negative dipole, and then there's an ion. So the dipole in this case is the water or the aqueous environment, because water has dipole moments, and then the ion is the phosphate from the phosphate head, which looks something like this. This is not the full thing, but it'll give you an idea. So here's the O with a negative charge, and then that's like the ion, and then the dipole. So it is an ion-dipole interaction. C. The hydrophobic fatty acid tails of phospholipids point toward the aqueous exterior of the bilayer to minimize favorable interactions with water. This is not true, and it's the false answer. Because hydrophobic means water hating, so it wants to minimize the interactions with water. And then this means that it points to the interior. So within the bilayer, it'll look like this. The tails are oriented towards each other in order to protect it from the aqueous environment outside. And then let's look at D. Bilayer formation allows for cellular compartmentalization. This is true. Just to give an example, well, compartmentalization just means being able to separate different parts within the cell. Example would be the nucleus, which is compartmentalized because the nucleus has a nuclear membrane, which is another lipid bilayer. Other examples would be Golgi apparatus, the endoplasmic reticulum, and many more. So that was the last question. Thanks everyone for watching, and I'll see you in the next video.